Welcome to the finale of the series. Everything we have built, vectors, matrices, eigenvalues, the spectral theorem, the singular value decomposition, converges today on a single, enormously useful technique, principal component analysis. Here is the central fact about real data. It lives in very high dimensions, thousands of features, but it almost never fills those dimensions. Instead, it clusters near a thin, low-dimensional slab, a few directions that carry nearly all the variation. PCA finds those directions. We will center the data, build the covariance matrix, and apply the spectral theorem to extract perpendicular axes of maximum variance, the principal components. We will see this is exactly the SPD of the data. We will reduce dimensions by projecting. Then we tour the applications that changed the world, eigenfaces, search, recommenders, and finally step back to look at the whole arc of this course, from a single arrow to the engine of modern machine learning. Let's begin. First, the setup. We arrange our data as a matrix. Each sample, a photograph, a customer, a document, becomes a row, and each feature, a pixel, a purchase, a word count, becomes a column. So a dataset of n samples with d features is an n by d matrix X. This is exactly the data vector from episode 1, now stacked many at a time. The problem is that d, the number of features, is usually enormous. An image has tens of thousands of pixels, a document tens of thousands of possible words. Yet the data rarely varies in all those directions independently. Faces share structure, documents share vocabulary. The true variation hides in a few directions. The goal of principal component analysis is threefold. Find the perpendicular directions along which the data varies most. Re-express each sample using just a few coordinates along those directions, and discard the directions with almost no variation, which both compresses the data and strips away noise. PCA is, in one phrase, finding the directions the data actually lives along. Step 1 of PCA is centering, and it is essential. First, compute the mean row, the average of all the samples. Geometrically, the center of mass of the data cloud, called the centroid. Then subtract that mean from every single row. The result is the centered data, every column now sums to 0, and the whole cloud is balanced around the origin. Why does this matter so much? Because PCA is about variance, the spread of the data about its mean. If we skipped centering, the analysis would be dominated by where the cloud sits in space rather than by its shape. A cloud far from the origin would look like it varies hugely in the direction of its own location, even if it were a tight little ball. Centering removes that distraction entirely. Once the mean sits at the origin, every direction's importance is measured purely by how much the data spreads along it. Centering is the quiet step that makes everything afterward meaningful. Let's make precise what we mean by the direction of greatest spread. Pick any unit direction W, project each centered data point onto it. The projection is just the dot product of W with that point. Now ask how spread out those projections are by averaging their squares. A short computation shows that this average squared projection equals W transpose times the covariance matrix times W. So the amount of variance the data shows along direction W is exactly the quadratic form W transpose CW. The entire goal of principal component analysis can now be stated in one line: maximize W transpose CW over all unit vectors W. Find the single direction along which the data spreads the most. But we have seen this exact problem before. Maximizing a quadratic form of a symmetric matrix over the unit sphere is the Rayleigh quotient, and the spectral theorem already handed us the answer. The maximizing direction is the top eigenvector of C, and the maximum value is its eigenvalue. PCA is variance maximization, and the spectral theorem solves it instantly. Step 2. Build the covariance matrix. Take the centered data, multiply its transpose by itself, and divide by the number of samples. The result is a d by d matrix called the covariance matrix C. Read its entries. Each diagonal entry is the variance of one feature, how much that single feature spreads. Each off-diagonal entry is the covariance between two features, whether they tend to rise and fall together. Crucially, C is symmetric because it is a transpose times itself, and it is positive semi-definite. Those two words should ring a bell. Symmetric and positive semi-definite is exactly the setting of the spectral theorem from episode 28. Here is the key connection. For any unit direction W, the variance of the data measured along W is the quadratic form W transpose times C times W. So asking which direction the data varies most along is asking which direction maximizes this quadratic form. And we know from the spectral theorem precisely how to answer that. The whole problem has quietly become an eigenvalue problem. Step 3. Apply the spectral theorem to the covariance matrix. Because C is symmetric, we can write it as Q times lambda times Q transpose, with perpendicular unit eigenvectors and real, non-negative eigenvalues, sorted from largest to smallest. These eigenvectors are the principal components. The first one, Q1, points in the direction of maximum variance, the single direction along which the data spreads the most. The second, Q2, is the direction of greatest spread among all directions perpendicular to the first, and so on down the line. Each eigenvalue tells you exactly how much variance lies along its eigenvector. Why does the top eigenvector win? Because maximizing the quadratic form W transpose CW over all unit vectors is a classic problem, the Rayleigh quotient, and its maximum is achieved precisely at the eigenvector with the largest eigenvalue. Then you repeat among the perpendicular directions, peeling off one component at a time. A useful quantity is the variance explained by each component, its eigenvalue divided by the sum of all eigenvalues. Often, the first few components explain the overwhelming majority of the variance, and that is the whole opportunity. Here is a beautiful unification that ties the last two episodes together. Instead of forming the covariance matrix, take the singular value decomposition of the centered data directly. X-centered equals U sigma V transpose. Now compute X-centered transpose times X-centered. The U transpose times U in the middle collapses to the identity, because U is orthogonal, and we are left with V times sigma squared times V transpose. Compare that with the spectral decomposition of the covariance matrix Q lambda Q transpose. They match perfectly. The principal components Q are exactly the right singular vectors V, and the variances, the eigenvalues lambda I, are the singular value squared, divided by the number of samples. So principal component analysis and the singular value decomposition are not two methods, they are one idea seen from two sides. In practice, we almost always compute the SVD of the centered data directly, because forming the covariance matrix first can square the numerical errors and lose precision. The SVD does the same job more stably. The decomposition we built last episode is the literal engine of PCA. Here is PCA on one canvas. Picture a scatter of data points forming an elongated tilted cloud, stretched out along a diagonal, not lined up with the horizontal or vertical axes. The small open circle near the middle is the centroid, the mean we subtract during centering. From that center, two perpendicular gold arrows emerge. The long one, labeled PC1, runs straight down the long axis of the cloud, the direction of maximum variance where the data spreads the most. The shorter arrow, labeled PC2, is perpendicular to it, along the thin direction of the cloud, where there is much less spread. The faint dashed ellipse hugging the points is the one standard deviation contour, and its axes are exactly these two principal components. The lesson is visual and immediate. PC1 captures almost all of the variation, so if we kept only the PC1 coordinate of each point and discarded PC2, we would lose very little. That is dimensionality reduction, replacing two numbers with one while keeping the shape that matters. In real problems, we collapse thousands of dimensions down to a handful this way. Two practical questions before we project. First, how many components should we keep? A common tool is the scree plot. List the eigenvalues in decreasing order and look for the elbow, the point where they suddenly flatten out, and keep the components before it. Or set a target. Keep just enough components that the cumulative explained variance, the sum of the top eigenvalues over the sum of all of them, reaches, say, 95%. Second, some cautions because PCA is powerful but not magic. Scale matters. If one feature is measured in millimeters and another in kilometers, the large unit feature will dominate the variance for a silly reason, so we usually standardize every feature to comparable scale first. PCA also only finds linear structure, straight directions of spread. If your data curls around a spiral or a curved surface, plain PCA will miss it, and you need kernel PCA or manifold methods. And finally, PCA maximizes variance, which usually, but not always, coincides with what is actually useful for your task. Used thoughtfully, though, it is the first thing almost every data scientist reaches for. Step 4 turns the components into actual compression. We keep only the top k principal components and gather them as the columns of a matrix Q sub k. To reduce a sample, we project its centered version onto these k directions, producing just k numbers, zi. We have replaced d features, maybe thousands, with k coordinates, where k is tiny. To go back, we reconstruct approximately, add the mean back, and rebuild from the k components. By the Eckart-Young theorem from last episode, this is the best possible rank AK reconstruction of the data. No other choice of k directions does better. The variance we lose is exactly the sum of the eigenvalues we dropped, the small ones. How do we pick k? We look at a scree plot, the eigenvalues in decreasing order, and find the elbow where they flatten out, keeping the components before it. The payoff is enormous. We can compress data, visualize 1,000-dimensional datasets in 2 or 3 dimensions, filter out noise that lives in the low variance directions, and dramatically speed up every model we run afterward. Dimensionality reduction is PCA's gift to all of data science. Let's run PCA by hand on a tiny dataset. 4 points in the plane, 2, 1, 4, 3, 6, 5, and 8, 7. Step 1, center. The mean is 5, 4, average the x-coordinates and the y-coordinates separately. Subtract it from each point to get the centered data, -3, -3, -1, -1, 1, 1, and 3, 3. Notice these all lie on a single line through the origin. Step 2. The covariance matrix. Form the center data transposed times itself and divide by 4. Each entry works out to 20 over 4, which is 5, so the covariance matrix has 5s in all 4 positions. Step 3. The eigenvalues and eigenvectors. This matrix has eigenvalues 10 and 0. The eigenvector for 10 is 1 over root 2 times the vector 1, 1, the 45-degree diagonal. The eigenvector for 0 is perpendicular to it. The verdict is striking: all of the variance lives along the first principal component, and exactly 0 along the second. The data, though written with 2 coordinates, is genuinely one-dimensional. PCA discovered that, and would let us store each point with a single number instead of 2, losing nothing at all. Now the applications that made PCA famous. The first is eigenfaces. Treat each photograph of a face as a vector. Flatten the image into a long list of pixel brightness values, so each face is a single point in a space with thousands of dimensions. Collect many faces and center them by subtracting the average face. Now run PCA. The top principal components are themselves images, ghostly, blurry face-like patterns called eigenfaces. The remarkable fact is that almost any human face can be reconstructed as the average face plus a weighted combination of just a few dozen eigenfaces. So a face that lived in a space of thousands of pixels is now captured by a short list of weights, maybe 40 numbers. Recognition becomes simple. Project a new face onto the eigenfaces, get its handful of coordinates, and find the closest stored face in that tiny space. This is nearest neighbor matching in a 40-dimensional space instead of a 40,000-dimensional one. Turk and Pentland introduced eigenfaces in 1991, and it was one of the first practical face recognition systems. Pure linear algebra, exactly what this course has built. 2 more world-changing applications, both the same idea. First, search. Latent semantic analysis builds a giant matrix counting how often each word appears in each document, then takes a truncated singular value decomposition. The top singular directions behave like concepts. Documents about the same topic land near each other, and so do synonyms, even when they never share a literal word. So a search can match by meaning rather than by exact keyword. Searching for car can surface a document about automobiles. Second, recommendations. Imagine a huge matrix of users against items filled with ratings, but mostly empty because nobody rates everything. A low-rank factorization approximates it as one matrix of user factors times another of item factors, latent dimensions of taste that the math discovers on its own, things like how much a user likes action versus romance. To predict a missing rating, you take the dot product of a user's taste vector with an item's factor vector. This is the heart of the algorithms that recommend films, songs, and products to billions of people. The engine, in every case, is ours. Take data, find a few latent directions, and project. Here is eigenfaces made visual. On the far left is the average face, the mean of every face in the dataset, soft and generic, no one in particular. Next to it sits a small gallery of eigenfaces, ghostly, high-contrast patterns, each a principal component reshaped back into an image. They are not faces of real people. They are the basic ingredients of facial variation that PCA discovered. Now follow the recipe across the strip. Start with the average face, then add the first eigenface scaled by a weight, plus the second eigenface scaled by its weight, and so on for just a handful of terms. The equal sign on the right shows the payoff, a recognizable, specific face rebuilt from the average plus a short list of weights. A portrait that began as tens of thousands of pixel values has collapsed down to maybe 40 numbers, the coordinates of that face in eigenface space. Store those numbers, compare those numbers, and you can recognize spaces with nothing but the linear algebra of this course. A short history to close the mathematics. Principal component analysis began with Carl Pearson in 1901, who framed it geometrically as finding the best fitting line and then plane through a cloud of points. In 1933, Harold Hotelling gave the modern statistical version, coining the term principal components and framing it as maximizing variance, the formulation we use today. In the 1940s, Karhunen and Loew developed the continuous stochastic version of the same idea for random processes. Then the applications arrived. Dearwester and colleagues introduced latent semantic analysis in 1990, and Turk and Pentland published eigenfaces in 1991. What ties it all together is that PCA rests on exactly the matrix decompositions this course built: the spectral theorem from Cauchy and Hilbert, the singular value decomposition from Beltrami and Jordan. It is old mathematics, more than a century old, endlessly reused. Every time a machine finds a pattern in data, it is leaning on ideas that were essentially complete before the first computer was ever switched on. Let's recap and then say goodbye. Principal component analysis is 4 steps. Center the data so the mean sits at the origin. Form the covariance matrix, which is symmetric. Diagonalize it with the spectral theorem. Its top eigenvectors are the principal components, the directions of greatest variance, and this is identical to the singular value decomposition of the centered data. Then reduce by projecting onto the top few components, which, by Young, is the best low-rank summary possible. That is PCA, and it runs eigenfaces, search, and recommendation engines. Now step back and see the whole arc of this course. We began with a single arrow, a length, and a direction. We learned to add and scale vectors and ask what they span. We solved systems with matrices and saw matrices as transformations. We built vector spaces and the 4 fundamental subspaces. We found eigenvalues and eigenvectors, proved the spectral theorem for symmetric matrices, and extended it to every matrix with the singular value decomposition. And today it all converged on the technique that lets machines find structure in data. One arrow became the engine of modern data science. Thank you for watching this series. That is linear algebra, the mathematics that quietly runs the modern world. Today, in the finale, everything came together as principal component analysis. We started with a data matrix, 1 row per sample, 1 column per feature. The first step is centering. Subtract the average row so the cloud of data is balanced around the origin. Then we form the covariance matrix, which is the centered data transposed times itself divided by the number of samples. That matrix is symmetric, so the spectral theorem applies. Its eigenvectors are the principal components, perpendicular directions in feature space, and each eigenvalue is the amount of variance along its direction. The top eigenvector is the single direction of greatest spread. The next is the best perpendicular direction, and so on. Keeping only the top few and projecting the data onto them is dimensionality reduction, and by Young, it loses as little as possible. We also saw that this is exactly the singular value decomposition of the centered data, so PCA and the SPD are 2 faces of one idea. That single idea powers eigenfaces for face recognition, latent semantic analysis for search, and the low-ranked factorizations inside recommender systems. And that is where the course ends. We began 30 episodes ago with 1 arrow, a length, and a direction. We learned to add and scale vectors, to solve systems of matrices, to understand spaces, eigenvalues, and orthogonality, and we arrived here at the decompositions that let machines find structure in data. Thank you for watching the whole journey. That is linear algebra, the mathematics that quietly runs the modern world. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.